Sorry.
Awesome. So we can continue. And this set of pairings of the input and the label that we want to produce is called training data. And uh, because we like this is like a little depiction of that, this is just that would be a linear model. So X is our input, Y is our label that produced by our model. And this function kind of can be called a model. And the goal of machine learning is to get this parameter theta that gets us the best correct Y. And the way we evaluate, when we get our parameter, the way we evaluate how good that parameter is and how good our model is by using loss functions. Uh, oh yeah. This is just visual intuitions of what I just told. Again, we can see like there's x-axis, there's y-axis. And if we just throw the data we have on the scatter plot, for example, we can see that it does show us some kind of pattern. And the goal of machine learning is to try and build those lines so that when I get a new x, I can just predict it to be on that line. And that would be a pretty accurate prediction because we see that all previous data kind of falls under that line. Yeah. And to evaluate how good that line is or how good our parameters are, we can use loss functions. Loss functions is basically a way to compare our true label with what our model gave us instead of the label. And since we're working with classification problems and we're going to be working with images, those are two most popular loss functions. The first, let's start with binary one. This is an equation that represents the loss um, when we have only two classes. So it's either 0 or 1. And the first one is the same thing, but when you have a lot of classes to predict. And basically what those equations mean is that Y is your true label, P is the probability of that output being that label. And the sum sign is the sum of um, all of those errors throughout the whole X/Y pairings of your data set. Also, feel free to stop me whenever and ask questions about anything, please. If you want me to repeat anything or yeah.
So basically this CE loss is like calculating the average of all like the probability errors across the data set.
Around that, it's not like exactly the average, but it allows you to understand how close your model was to guessing the actual true label, and that's kind of the goal.
And what is PIJ?
So PI, let's start from the beginning. So let's say you have n data points. By that I mean like X/Y pairing, so X and its corresponding label. And then in the equation, you have YI. I is like your current X that you're looking at, your current data point that you're looking at. Y is that's true label. P is the prediction that your model gave you for that label. And then the sum is because we want to calculate that thing inside of the equation for the whole set of x's, not just one. And then we divide by n because we want an average of all x's, kind of. Does that make sense? And yeah, just to add, for the categorical cross entropy, J would mean that like because we have multiple classes, we will have instead of like a binary true false or like binary class thing, we will have a list of different probabilities of what that particular data point could be. And we also sum across that as well for each of the x's. Does that answer your question?
Yeah, it does, thanks.
Okay, nice. Any other questions about that? Okay, yeah, if you have questions about it in the future, feel free to also ask about anything in this presentation. There's also a message in the chat, I wonder. Oh, that's nothing. Okay. What did I close that? This, I think. Yeah. So yeah, we talked about how we use loss functions to understand how good our model is. And the purpose of that is so that because we don't know exactly what those optimal parameters for our functions are, we want to try out different parameters. And the question is, how do we understand, like, if I have a certain parameter theta, and I have some certain output of my loss function, how do I minimize that loss? So how do I minimize the error that my model creates? And there are different algorithms to optimize the loss value, so minimize it. One of which we're going to talk about is gradient descent. And what it does is like the first one is like the general equation. This is like kind of our model, right? There is our x, the data point. Then we have m and b. It's kind of the same, like let's m and b is kind of theta, the same thing as I was talking about last time. But this time we have like kind of m, which is the weight for x, and b is like a bias parameter that just allows us to like adjust the scale of y predict. It doesn't matter what the input is. So yeah, if we have our model in one, we can create a prediction of y, and then we can calculate loss using our true y versus predicted y. And then we can graph those, um, and we can graph the output of the loss functions depending on our parameter b and our parameter m. And this is going to look kind of like this. Because we have two parameters in this equation, that's why it's kind of 3D. And the y-axis here is the output of our loss function. And because our goal is to minimize the value of loss function, so minimize the error, we kind of want to reach that like blue region. So we want to discover what parameters of m and b would give us the blue output of function L. And to do that, we use derivatives. So we would find the derivative of function L and try to minimize it. And because function L most likely in complex models is going to have more than one variables, we will call it gradient. Gradient is just derivative, but for multivariable functions. And because gradient gives us the direction, so gradient is a vector that would give us the direction of increase of the function. We know that if we go in the opposite direction of the gradient, we know that we will kind of go down, down, down until we reach some minimum. It's not guaranteed it's going to be like the minimum parameter. That would be too good, but we will reach some local minimum over there. That's kind of more pictures. So you have theta 1, theta 2, the same thing as b and m, like I did on the last slide. And this kind of the graph of our loss function again. And we can see if we start at a certain point using this gradient descent rule, we will try out different theta parameters, and at a certain point we will reach some minima that will be better, hopefully, than when we started out. Yeah, so this is like the summarization of the gradient descent algorithm. By the way, do you have any questions about that at all? Or you good? Okay, we can continue.
What's M? Is that what you're using for weight
Yeah,
for bias?
so basically, yeah, here I just said like theta in the beginning. If you just like a summarization, let's say theta is just a vector of all your weights and parameters and like in general. But over here, yeah, I just kind of splitted them into which is M, which is the weight for X, and B is the bias, and which is just influence the scale of the output, what predicted if you want to scale it kind of, and you don't want it to be dependent on your input. Yeah, and here's also the same thing. You can choose different B's, you can choose different M's as well. Yeah. Yeah, and gradient descent allows us to use those gradients to adjust parameters to make the loss function be like the value of loss function be smaller and smaller every single time. And we can repeat it as much as we want. Yeah, so machine learning means that we can create some function, so what we call a model, and the training would mean that we want to count and minimize the value of our loss function. Yeah, and one way to find this minima is using gradient descent. There are other algorithms also, but gradient descent is kind of, I feel like, more classical. Yeah, and now we can talk about neural networks. So neural network, basically, you can treat it as like a very complex function. There's a lot of things going on, but essentially it does the same exact thing as what I showed before. It just a lot of weights, a lot of stuff going on. But essentially what it does, you have your input, it goes through that model, and then you get your output. And then you do the same exact thing with where you compare the output with your true labels. And then you also can calculate loss and understand and then adjust those a lot of parameters that are happening in the neural network. And I will explain a bit more. So yeah, neural network consists of a bunch of layers. The first one would be input layer, then there are hidden layers, and then the last one is your output layer. Input layer always have the same number of nodes as your input does, and your output also should always have the same number of nodes, like number of classes that you want to see. But yeah, the picture on the right shows you kind of what happens in each individual node. Each individual node receives inputs. For example, for the picture, let's say each individual X would be a pixel. So over here, each node receives every single pixel and then does some kind of transformation with it. And the transformation it does is like the Z thing that I wrote, like this formula. So each X is multiplied by its own specific weight, and then everything is summed in that one node. And after that, to add some nonlinearity to the model, this sum goes through what we call an activation function, and I will talk about it a little bit more later. Yeah, and so every single node does this type of operation, and then in the end, it kind of leads you to you have like, in this case, you have 10 classes, you have 10 outputs. And the outputs would be probability of that specific picture being of that class. So here we chose 7 because it was an array of 10 numbers. And the one that corresponds to probability being 7 was the highest, so we chose 7. Oh wait, let me ask. Do you have any questions on this?
Can you repeat so you said the same number of, your input layer needs to match your out? Your effect.
Yeah, so whatever happens in hidden layers, so in 2 layers in between, is kind of very adjustable, and you can experiment with that. But your input layer and your output layer are kind of fixed size because your input should always be standardized. It should have all your inputs should have the same like number of things in it. So if it's an image, it's going to be an image of like, I don't know, 200 pixels. And each pixel is going to be like a specific individual X. That's why in that layer, for example, it says 784. It means there are 784 pixels, let's say. It could be just like RGB values, for example, not pixels, but yeah. So that would be fixed. The first layer number of nodes is going to be the same as how many inputs you have.
The layers aren't fixed.
Yeah, those you can adjust those. You can have multiple hidden layers, not necessarily 2. You can have different number of nodes in those layers. You can also adjust the activation function. I'm going to talk about that. But for the output layer, you should always have also as much nodes as much as you expect outputs. Question?
Are the weights determined?
I'm going to talk about it a little bit, but essentially, there are certain weights that you kind of start with that are arbitrary. And then you train your model on the data. I think I'm going to talk about it in the future. Or maybe not. Yeah, I was going to talk about backpropagation. So, oh, that's not the right one. 1 second. But yeah, backpropagation is an algorithm that after you put your inputs in the yellow input layer, it went through your model, it gave you some kind of output, and then the first step is you calculate the error using your loss functions. So you compare the true label and the output, and you see how big the error is. And then you go in backwards direction and you calculate those gradients that I was talking about. And then you use gradient descent and choose a better parameters for each of those nodes, and you update them. And for every data point, you will do the same thing, kind of, and that would lead to you updating all those parameters using gradient descent, and then it will be kind of better. And I feel like you can see, we will see when we do the collab. Usually when you train your model, it does show you like current loss, just current loss. And you see that it like decreases if your model is good. Does it answer your question? Or you want to clarify kind of? Okay, that's good. Yeah, I stopped here. So yeah, the layer parts, it's kind of, yeah, what I kind of mentioned. So we have our input layer. Every node has some weights associated with it. And then there's a bias vector, that's the little b that I said. Like, so weights are corresponding to their specific x. And b is just like plus b in the end. It's called bias. And it allows you to scale your input depending on your needs. So it doesn't depend on the input. So if you input it all 0, but you don't want to output 0, that's where the b is useful. Then activation function, I'll talk about that. And output vector, that's going to be your output that you get after the neural network is done. And then, yeah, activation function, as I said, the purpose of it is to introduce the non-linearity to the model, which allows us to do kind of things like this, where if we have data that is clearly non-linear, but also like divisible like that, it allows us to adjust to that. That's why we kind of always have an activation function in the end of our node calculation. And there are different activation functions. You can also, for each node, for each layer, kind of, you can adjust what activation function you're using, and it will also kind of give you different results. I think, yeah, I would recommend just trying out different ones usually, but sigmoid is like good, for example, for binary classifications, because you see how it makes data points be like on a very different kind of edges. So the probability is going to be, how do I say?
Activation functions and then
Technically, yes. So you would have, not, I believe that like the libraries we're going to be using, basically you specify activation function for that one layer. So like the whole layer of those nodes is going to be using that one activation function. We're not going to write anything of this from scratch, by the way. We will just show you how to do it using like PyTorch. So yeah, this is about activation functions. And then I wanted you guys to try this link out. It's like an exercise or a playground where you can try and get a feel of how it is to build a neural network. And over here, there's an input layer, there's an output layer. You can increase the number of hidden layers. You can increase the number of neurons in the middle. You can choose different activation functions for here. Like here, you can choose activation. And then to train your model, you would just do this. Well, I didn't mean to do that. I just randomly clicked and it fits, honestly. But yeah, so there are like 4 different like distribution of data you can choose from. And then when you train, you will see that like
Yeah, they're just right there. Okay. That one's for painting.
yeah, the goal of the exercise is to
Okay.
those dots are those are the labels. So the blue label there's storage label. Your model classifies it as. And you can consider it for different and the goal is to match the background how I did absolutely randomly. The play button, and then it will show you. So spend like 5 minutes in that, and let me know if you have any questions.
Right, you talked like how many times the back propagation went loose.
The number of times the model goes through the whole data set.
Okay.
So it went through the whole data set. Once adjusted the weight, so you can do it again and try to adjusting the weights again. So each of the number of times going to happen. It's like this Furby thing. I would be curious to see that. So let me know if that. And if you're really discuss with you as well. Then I don't know.
Good. No?
Well, like one thing is later means one is reading. So in clear is one is reading. It's really possible to like make giving people because depending which part of it doesn't really make sense. The teacher is clear kind of represents a certain thing. So if you were like specifying the like the logic is that the words the same way in all the world. So first you have a big Saturn, you break it down into smaller letters, then smaller and smaller letters until you can get a and it's the same thing like a year. One layer is kind of the same logic that it's like the pattern of this size. The next layer is kind of like small size. So that's why usually one layer is the same tissue. So first thing feed forward the important there will be showing and then we'll see like how to make this. I'll be talking about one of the so we just we're just gonna that one is next gen. Yeah, we'll talk. I'll talk about that a bit. I think I talked about it already because someone asked me. Yeah. How do I? Yeah, I don't know that. Okay. I just closed the tab. Yeah, you could just close the tab when it's done.
Oh. I don't remember.
Yeah, I think we can continue now, but yeah, I think I briefly explained backpropagation when someone asked me about it. But yeah, essentially backpropagation is this process of getting your error, like the value of your error, and going backwards, calculating the gradient of your loss function, and then using gradient descent or any other optimizer, you update the weights, and then you try and um, like put your data through the whole model again to see how much your loss function has improved. And that's basically what the training of the model means. Yeah, so it's kind of the key takeaway. We have forward propagation. That's when the input data goes through all the layers and generates some output. And then computing loss is when we use that formula to compute how different was the actual output, the probability of our true class versus the true class. And then we apply the chain rule to calculate the derivative of the loss function for this like whole big set of parameters and just tweaking them a little bit as we go backwards. And then we can do this whole process again to adjust our weights even better. So yeah, I can pass it to Rebecca for a little bit of recap for the portion that we didn't get the chance to cover last time. But if you have any questions, just do you have any questions first of all? Or okay, awesome.
Okay, so does anyone know what backpropagation is? Oh, would someone like to volunteer? No, you're all too shy. Okay. Huh? Oh, okay. Could you say oh oh sorry. Thank you.
Backpropagation.
That process of updating your with network. So once you calculate your once you like calculate your losses for all the inputs, then what you want to do is go back to your neural network, calculate the gradients at each step of the process. And you want to calculate the gradients of your weights and bridge it back to the loss. So and then once you do that, you want to like use those gradients to update your original weights.
Okay, thank you for your explanation. So to recap, so for the forward pass, remember we say there will be like a randomized set of weights. So I think someone asked like previously, like how will we learn from like a randomized set of weights? So the key thing to remember is, so in our context for this lesson, we're talking about supervised learning. So what we meant by that is for our data sets, we always have the answer for each of the questions. So it's a bit like you have your Quizlet, and for your Quizlet, you have the front card and then like the back card. So you have access to both the question and the answer. And then so you know like what the answer will be. So with this kind of problem, what you can do is you first let the neural network use like their original weights, and then they try to predict, like they try to give out an answer. And then after they give out an answer, you will look at the training data set for each of the sample, and then you will see if they reply correctly. And so here's where like the loss comes in. So if like they are totally wrong or incorrect with like their answer, the loss will be really big. So what we meant by that is when the loss is really big, when we do backward propagation, the update of all the weights for each node will be really big. So there's also another like habit parameter called learning rate of how much you want to like change your gradients. But this is like how it works. So it first go through 4 paths to like compute like an answer for example, classification. And it looks at the answer in the data set. And then based on whether it got correct with the data set, it updates itself with the weights. Okay. Yeah. So yeah. Any questions so far? Okay, so I think last time we left off from data pre-processing. So this time what we're gonna do is we'll go over like the answer code or like solution code for that, and I will briefly go over like the entire rationale for like transforms. And then next Aniruddha will cover PyTorch tensors and why tensors are important. It's like the data type that we'll be using. Okay, so I just added the solution code for the data transformation, data pre-processing into the AI School 2 collab. So I will be running from this. Oh, and to recap on why we want to do data transformation, it's because when we load our data sets, there's something called transforms in like one of the arguments that you can do to like apply transformations to each samples within the data set. So that you do some kind of pre-processing for that, so that when the machine learning model is learning the things, it's like a lot easier than when they are learning from like the raw images. Yeah, because sometimes like they will look really different. Yeah.
Yeah, there's the link.
Oh, okay.
The
I think it's here.
Yeah.
Yeah, so here's a link to the collab, so feel free to make a copy of it. And you'll already have the solution code for data pre-processing or data transformation, to be more specific. When you're finished with copying the notebook, look at the, I don't know, look at the podium, I guess. Oh, by the way, can anyone remind me why we're using Google Colab instead of running locally?
It's easier to do.
Yeah, it's easier to do. And then also Google provides like for Google Colab.
Yeah, they have like the GPUs.
Yes, they have the yeah, cloud GPU for you to use. So we can go over that again later to do like a refresher.
Oh yeah, and if you want to like when you work on this and you want to edit it and want to save it, please make a copy of the original document. Because the one that we have here, if you just directly edit on that, that will not be saved.
Yeah, make sure to make a copy. Is everyone done with making the copy? Okay, so I will interpret that as everyone's done. So let us click into the link. Okay, so to recap, so here is the runtime, and what I meant for like the GPU is if you go to, oh,
You should make a copy too.
I should make a copy too?
Yeah.
Okay.
So the original one is unchanged.
Oh, you're right. Okay. So here you will see connect to T4. So here's like your runtime type. So what I meant by that is if you go to runtime, the menu, and then in the runtime, there's change runtime type. So here you will see like first the runtime type, it includes like whether you want to run Python or R. So R is another programming language. So this might be really different if you use R for this notebook. It might not run. And then for the hardware accelerator, you will also be selecting between CPU, T4 GPU, and TPU. So the CPU is I guess running like your own computer's CPU. And then the T4 GPU, I think it's for the they're using Google is cloud hosting the Tesla 4 GPU, I think. So when you use this, they basically give you like a limited amount of time to have access to this. So that when you're running PyTorch, you get to run it on GPU. And then the other one is called TPU. It's I think it's different from GPU. Yeah,
Tensor processing? Is that what that stands for? TPU?
I think so.
I'm not sure for like the exact name. Yeah.
It's a processing unit and
Isn't that like, I thought that was like the
it's
Google.
only, it's only exclusive in Google, so they don't sell. Yeah, you're right.
Oh, really? I thought like since Apple has like a huge beef with NVIDIA, they are starting their TPU.
So it's not the same thing.
Okay, yeah. So I see. Yeah. So here's like different kind of hardware. So yeah, that's why we also use Google Colab. Yeah. And so with regard to like the data preprocessing last time, remember we all of you chose like the image that you like. Yeah. So here for the image, I chose like a corgi. Yeah, since like it's a default one, I guess. So here you will type in wget. So first, since I want to save the file, so here if you click on the files, you will see that there's like a folder structure here. So here I wanted to save the image in a folder called assets. So I first run the command make directory. Is it big enough? So I first run the command make directory to make the assets folder first, and then I run something called wget. So wget like downloads the thing from this given URL. So for my case, this URL contains the JPG file for the corgi. And then after this, we use like a flag like hyphen capitalize O, and this is like with this flag, you specify where your output will be. So for our output, it's in content and then assets, and then the name will be doc1.jpg. So for you, you can choose whichever file name you want. Yeah, does that make sense? Okay. Yeah, so let's run this command first. Oh, and then when you're running the cell, you can use like a shortcut, shift return or like shift enter, and then I guess that will help you save time. Yeah. So here, after we run the cell, we can go into, we see that the assets folder is being created, and then here's the doc.jpg file. So this is what it looks like. Yeah. Is everyone on the same page so far? Has everyone used their own URL and then downloaded it to the folder you like? Okay, I think everyone is done. Okay, so the next thing, so last time we talked about like how we can read the files and then use the transforms. We use like multiple kind of transforms. We use like compose and then we put the image inside. So I think instead of doing like coding, I think I'm just gonna run through like the thing, like what this is doing. So you already have access to the solution code, so I'm just gonna explain it. Yeah, so first we import like the libraries that we will be using. So here the first thing is we read the image. So this read image function is given by torchvision.io. So we import that first. We import this function first so that we can use this function. So next, so in read image, it needs an argument that takes in the path. So what we do is so this is called we use something called OS. So OS is like you basically use that to deal with like different kind of path. So we use OS path.join assets and doc1.jpg. So the reason for that is because the folder the doc.jpg is within a folder called assets. So that's why we're joining them together. yeah, I guess what we can do is we can print this too. So you get a better understanding. Let me comment these out first. Oh, is someone gonna ask questions? Okay, no, they're not gonna ask questions. So here is what like the OS path.join will give you. So this is just like the string of the path. So we first re-image from that, and then remember last time, I hope you all went to like the first workshop, but last time what we did is, so after we image, we first permute the image into so after we do re-image, what it will be giving us is the number of color channel and then the width and the height. But then that is not what matplotlib.pyplot wants. So the structure it wants is instead we are starting with index 0. So index 0 here is the number of channel, and here is the width and the height. So we use permute to switch the order, so that the first one for the shape will be the width, and then the second one will be the height, and then the third one will be the number of channels. Because so the channels are RGB because the corgi is like colorful right now. Yeah, so that's like the default one. Yeah. So that's why there's like 3 channels. Okay. So I guess for the next thing, I'll just do like the transform first. So for the transform, here what we define is we first change the input image into tensor format. This is such that it's like faster for computing, I guess. And then the next one is because after we read in the image that's being read in will be in uint8. So that's unsigned integer with 8-bit up, right? Yeah. So that's like another format. That's 0 to 255. But then we don't want that. We want the range to be between 0 and 1. So we change it to flow32 with the scaling applied, so that it's the range of the number is being applied, so that it's being a flow32 number, because flow32 is what we want when we're pre-processing. Yeah. And then the next thing is we do random cropping. Yeah. So these are like the 3 things we are doing with our transformations. And then with what compose does is that it combines all our transformations together, so that when you combine them, when you want to use this set of transformations, what you do is you call transform. So here we can see we can do this. So transform is now a function that consists of all of the transformations that you will be applying. So these 3. And then what it will output is a transformed image. Yeah, does that make sense so far?
Yes.
Okay. Yeah, you're gonna ask a question.
So transform count, is it just basically enlarging it? You know, it's taking like a segment of the original image, because I printed it out in just like it's like a small like segment in its background or something.
Oh, yes. And that's because we are randomly cropping any area within the image, and then the random crop size is 128 by 128.
Okay.
Yeah. So remember here when we were printing out the width and height, it was originally 500 by 500. So that's like the width and height in pixel values. And now we randomly select any part of it that's that size. So that's why the output is like that. Yeah, so I guess you can also try it with commenting out the random cropped, and then you will see it's not being cropped. Yes. Okay, I guess we can also plot the transform image. So here's a transform image that the person just mentioned. So here's like the so originally the corgi looks like this. This is like the full picture, but then after we do like the transformation, it's randomly cropped. So the image transform, the size is 128 by 128, because here we specify that the final size will be 128 by 128. Yeah. Okay, so here's like the subplot version. Oh, no. Yeah, does that make sense so far? Okay, any questions? Okay, so next we're gonna go into tensors, but then I think this will be quite useful when you're looking at your transform image, so that you can test with your your set of transformations that you're gonna apply to the image. So I guess leave this code in your notebook, like maybe Command save or Control save, and then maybe you can experiment with your different transforms later. Yeah. So I think Aniruddha is gonna cover it, cover tensors later. Maybe like right now.
Okay, yeah. Okay. So let's start with a small group activity. Yeah, does anyone know what a tensor is? And if you don't, I think you can just all kind of discuss within yourselves. I'll give you guys like a minute or so, and then I'll call on someone. Okay.
Oh, there's a cell in the collab notebook on this exercise, so you can also look at the instruction there.
No, I'll go into that a bit later. It's basic.
So like for me, like they have like.
I mean, they can use.
But for tensors, and what you can do is you have.
Yeah, I'm most familiar with that, actually.
And some of them is like.
I need to actually.
All right, so we'll come back now. Or okay. Yeah, okay. So basically what tensors are, like he said, they're like matrices on steroids. So we have so okay, so a scalar or a number we might use more in programming is one type of data. Then we have a vector or an array, which is basically like a list of those numbers. And then we have a matrix, or what we call a 2D array, which is a list of lists. And then we might have a 3D array, which is a list of lists. And so we kind of need some sort of generalized version of that. And that's basically what a tensor is. So they're just multi-dimensional arrays that are generalized from matrices. So what we would call 2D array, 3D array, we can just call them like an ND array. And over here, like there's a small table here. So a scalar or a number would be a 0D array, and then the vector would be a 1D array, and then so on, matrix 2D array, 3D array, and then basically ND arrays. And that is going to be very useful, as you will see later on, when we go more into building our model. But yeah, they can hold different types of informations that can be useful in neural network. And I'll show you a couple examples after we go to the next exercise in the Colab. And then yeah, you'll see them like properly when we implement the network. So if we can just go to this tensor section here. Yeah, is everyone, sorry, maybe I'll leave the link up a little longer. You guys, does everyone have the Colab? I can see a couple people have it, some people don't. Okay, you guys ready to start? Awesome. Okay, so now we are in the Colab. So this is just like a very short exercise so that you guys kind of know some basics about how to use tensors in PyTorch. It's going to be very intuitive because it's basically like there's nothing too technical here. So I just wanna, I guess, start. So we start with importing PyTorch. Ooh. Um, what are you supposed to do in this situation? Can I terminate? Or maybe, oh no, I'll we should take a copy. Or, okay, awesome. So yes. So now we're just going to create a simple tensor. Um, some does anyone want to just like make up a tensor right now? Or like we could just do like a 2x2 tensor with like, let's just do a basic 2x2 tensor. Oh, shoot, it's called. Okay. So we'll do tensor, which will be the creative name of our tensor. And we'll do torch.tensor, which is the call that we'll use from PyTorch. Okay. And then in that, we'll basically create our tensor. So if we want to do a 2x2 matrix, which would be a list of lists, a 2D array, we start with this one list, and then we'd have to have two lists within this. So let's just say we have 1 and 2, and then the other one is 3 and 4. All right, is everyone happy with this? Okay, so now we can run this. And yeah, now we've created our first tensor, and it's a 2D matrix with the variable tensor. All right, so that's how we created the first tensor. You guys are, let me know if you guys want me to go faster or slower or whatever it is. And feel free to ask any questions. Okay, so now we want to do a couple of operations with tensors. So like, how we do with arrays, we can add, we can multiply. If you've done Math 18 or any linear algebra before, you kind of know how we can, add and multiply. We can also divide and subtract, but this is just generally what we use as examples here. And again, the purpose of showing how to add and multiply is you might not necessarily have to add and multiply tensors like explicitly when you're building a neural network, but the idea is that it would be very useful if you ever need to, and it's kind of a bit more of an under the hood type of thing. So we can create two tensors. Does anyone want to volunteer to create another tensor? Yes.
5, 6, 7, 8.
Ooh. Okay. So let's call that tensor A. And see, I know it holds mic. Okay, I'm just gonna type for a second. Okay. Okay, so that's tensor A. Let's do tensor B. A lot of the times with these, the Google Colabs AI is really, really good, and it'll just write out the whole thing for you. So I'm trying to avoid that. So I can write it out fully. Um, let's just do something random again, like 2, 3. Let's go a bit. Let's do some odd numbers. 7, 11. Okay, nice. So now we have tensor A and tensor B. Maybe we'll put this in a separate code block here. Okay. Okay, so now we have our tensor A and tensor B. So then if we want to add these, does anyone want to say what our addition of these two tensors would look like? All right. Okay, so it should just be I mean, oh yeah, oh sure. Are you at the back? Yeah. Yeah, that's what the code is. So the answer B, we could just return this, but let's just assign this to another variable just so that we can I just wrote tensor sum over here. But in Colab, you could just run this straight up and you should get an answer. For the tensor multiplication, it's the exact same thing. Tensor A into tensor B. And yeah, you can just assign this again to the, what did I name the variable? Tensor mod. Okay. Yeah. Okay. So yeah, basically what we get here, what we would hope to get here is, well, I'll just run it first. Okay. So as you can see, the addition was just like straight down. You see this 5 plus 2, 6 plus 3 gives 7 and 9, 7 plus 7, 14, 8 plus 11, 19. And then the same thing with the multiplication, it just multiplied it down. 10, 18, 49, 88. You could also do this with different kinds of tensors that don't have to necessarily just be 2 by 2 matrices. Even within a 2D array, you could have a 2 by 3. You could have, you could have like a 2 by 10. It could be anything. And, again, if you've done linear algebra, you kind of know which matrices you can multiply by which other kinds of matrices. Again, it's not super important for you to know this right now, but it's just, this is like a very limited example, and there's a lot more that you can do. Okay. So the next thing that we want to do is, yeah, I hope everyone got this. If there's any questions, again, let me know. The next thing we want to do is reshape a tensor. So that's basically, we take one of these tensors and then just kind of like squash it or flatten it. And the use of that is maybe sometime our model would be better with a different kind of shape for a tensor. So if a network only accepts like a 1D array, then we might want to change one of our tensors to kind of have a different shape so that it works with the model better. So we could just take we can just take our first tensor here, 1, 2, 3, 4. And let's say we want to make that into a 1D array. So it's a 2D array right now. And we just want it to be like one list of basically 1, 2, 3, 4. So there's a very easy operation for this. So yeah, reshaped tensor is what I'm naming this. And it's actually a very easy operation. It's just tensor.view. And so since we have like, it's a 2 by 2, we'd want it to be 1 of 4. So we could just do, yeah, we just do that. And then we have 1, 2, 3, 4. If you want to try running 3 on this, you'd see an error because, there's 4 spaces. You can't have it be 3. And then there's another hack that I've learned where you can just do -1 and you get it directly. So let's say you don't know exactly how many spaces that your your tensor has. You don't know that it's exactly 2 by 2. You don't know what it is. Could be 2 by 3, 2 by 5. If you just do -1, then you automatically get it. You don't have to put 4, which would mean 4 spaces. If you do -1, it'll automatically flatten it to a 1D array. That makes sense. Okay. And let's just quickly shape the same one back. We had done 4 on this one before. So I'll just copy this. Oh wait, no, yeah, it's fine. Okay, let's do new tensor. Okay.
Reshaping it, like change the values of that?
No, so as you can kind of see here, the first tensor, so we just ran it on the same tensor as the first one,
Yeah.
which was just 2 lists. One was 1, 2, one was 3, 4. And then by reshaping it, we just made one list of 1, 2, 3, 4. So the values remain the same, just the shape and the structure that changed.
simplify.
Okay. The next thing we want to do is just kind of get it back to that original tensor of two lists, 1, 2, 3, and 4. So we just do tensor dot view, and then we do 2 and 2. Oh wait, no, we shouldn't do it on tensor dot view. We should do it on reshape tensor dot view. Yeah. Okay, and now you see we got it back. We got our original too far. 1, 2, 3, 4 back like this into two different lists. So that's basically it for the very basic operations on tensors. Here's just another way. This is, I'm not gonna live code this one, just because again, you probably won't have to do this specifically. And we'll get more into like accessing GPUs and using CUDA in the next part where we actually build the model. But I can just explain what this code is doing really quick. This first line is device is equal to CUDA if torch or CUDA is available, else CPU. So basically, what this line is doing is checking if a GPU is available on the cloud of Google Colab. And if it is, then it's assigning the variable device to CUDA. And if you assign the variable device to CUDA, it means that you're now running on the GPU. And if the GPU isn't available on the cloud, then you're assigning it to run on the CPU instead. So the big benefit of using tensors is that you can kind of seamlessly transition between CPU and GPU. And that's really helpful because, obviously GPUs are much faster, they're expensive, but, if you can, they have like parallel processing, which allows you to, go much faster and makes it really useful for neural networks and stuff like that. So this next line basically tensor on device. So device is whatever we chose, CPU or like CUDA, which would be the GPU. And then we just basically put the tensor onto that device. So if we run this, then, okay, so we saw that it was on CUDA. So right now the tensor would be running on a GPU. You don't need to know this like super well. I just kind of want you to get like the high level of it. So yeah, don't worry about that. Let's just, if there's no questions, I'll just go back to the slides and then we can quickly talk about why this is important. Okay. So what kind of data can tensors store? So tensors could hold input data like images, text, or any structured data fed into the network. Like I mentioned before, you might want to, reshape the data so it fits better into a model. It could also store the weights and biases in each layer of a neural network. And then during the training, tensors could also store the gradients. So, I mean, as you saw, like it's basically, I mean, machine learning is basically just like very glorified stats and calc. And it helps to have like the partial derivatives of each thing so that it's the most compatible with training neural networks. So that's what you need to know about this. So a tensor could store many different kinds of things, and that would include the derivatives of anything you need during training for the gradients. The reason that tensors are important for you to know is that they're basically very foundational in any deep learning or neural network that we want to train. So it's like the most foundational data structure you need to know. They also allow for really efficient storage and manipulation of multidimensional data, like I just showed you. So with images, you might have slightly different tensors or values based on if it's a grayscale image or a color image, you would have 3 different streams for red, green, and blue versus, grayscale would just have 1 stream. And then, like I mentioned in that last part, the importance of tensors is that you can really seamlessly transition between CPUs and GPUs. And I think that's what's, really powerful about it. So, you can, it's kind of modular because you can change it easily. So for the next part, we're gonna go back to Rebecca to build, your first model with PyTorch.
Okay, so as a recap for the why tensor is important, the other reason for PyTorch tensor specifically, it's really different from NumPy because NumPy doesn't support running on GPU, so it doesn't have like optimization on GPU. So that's why a lot of like the NumPy, all like the NumPy libraries, they if you want to support GPU, you either load them onto like PyTorch, transform them into PyTorch tensors first and then run the things, or you just run it on CPU. So it's like really different from like, yeah. So for NumPy, you will not be running them on GPU, a selected device. So it might not be the best idea to run like distributed like programs with like NumPy because they will be really slow and that will cost like a lot more money. Yeah. So the next thing is to build a fully connected neural network through PyTorch. So if you look at your Colab notebook, there's a section on that. So I guess the first thing we want to do is so the first step, remember last time we imported, like we loaded the data set and we also have the data loader defined. So I think that would be the first step. So on your Google Colab notebook, so here, these will be from the previous section. So with transform, use the transform you defined like last time, or use the transform you defined like with the solution, kind of semi-solution code. So yeah. So first do that, and then the next step is to define the data loader. So remember last time we went to the documentation, Torch Vision datasets. So that will help you like know how you should be loading the datasets. So I guess this will be like a small activity first, and then also like a review from the first workshop. So I guess this will probably take, let's do 5 minutes first, and then see how everyone does. Yeah. Okay, so as a hint, so what you will want to do is you will first want to search for Torch Vision datasets, and under Torch Vision datasets. So in this lesson, what we want, the datasets that we want to use is called the USPS dataset. So the USPS is like the when you do like Amazon or something, they're gonna like ship you the boxes, right? So the USPS dataset, they contain like the digit recognition datasets. So that's number from 0 to 9. And then you want the machine learning model to use the data to do digit classification of like, oh, is it 0 or 1 or 9? So what do you want to do first? So since for PyTorch, for Torch Vision, they already created like the data loader and the data set for you. So please go to the documentation site. So that's PyTorch, and then go to Torch Vision datasets. So here, they already have the built-in datasets. And then we can look for USPS. Oh, sorry, it's here. So within the datasets, there's one called USPS. And so our goal right now is to get the dataset from this and then the data loader. And then for the dataset and data loader, they will be different for the training one and the testing one. So to make an analogy for when you're training, what you will do is like for supervised learning, like what we're doing in this case is we first want you to like go through like a practice exams and then do them and then receive feedback from the answers that you the professor give you from the solution key. And after that, during your actual midterm, they will be doing the testing data set. So in this case, the testing data set, and then they will be looking at, they will give you the test, and then they will not let you know about the answer. So you will be evaluated, the model, like in this case, will be evaluated based on how they perform with the test data set. Yeah, does that make sense so far? So that's why we want the testing to be separated from the training. So what we do usually is we get the entire data set and then we split them into training and testing. Yeah. So please do this first. Yeah, so here's some Python syntax. So here I added like this. So after the colon, it specifies the data type that you will want this thing to have. So you want your trained data set to be some kind of like torch.utils.data.dataset. So another way you can look for how to find this is to maybe go to the datasets and then look for how you can be loading them. So for example, this will probably be one of the how you can use the data set, and then here's the data loader. But then for this, like the caveat is you want to split them by either their training or testing. Yeah. So, okay, so the next thing is to since we go to USPS, we will find that there's a tag called where is it? Chain. So if we go to label chain, so the chain, if it's true, it will be the training one. And then if it's false, it will be the testing data set. So what you want to do is you want to call this thing and then specify. And then for the two data sets, for the training one, for the chain tag, have true for that. And then for the second one, for testing, have false for that. Yeah. Does anyone have any questions? Oh.
Will the answers to this be available later on?
Oh, yes, I'm gonna code that later, like in a few minutes.
Okay.
Okay, I think I can provide some other hints. Wait. So if we go to here. So here will be some kind of like hints for how you can do the data set. So in this case, they're using the fashion MNIST data set, and then they set the chain equal to true for the training data, and the chain equals to false for the test data. So yeah, so in the case of USPS, this will be really similar, but just with different kind of data sets. Like for this one, you would probably write something that's related to USPS. Oh, I think the timer has elapsed, but it included the time for giving hints. So would it be good if I use another 5 minutes, or would you want me to go over like the solution code? Oh, yeah.
I have a question for that. Well, like, there's like a cell right above it where you do for torch vision, or from torch vision, you do for data sets and transforms. And then there's a bunch of like, variables that look like the definitions. And then like, when you import the data set, you need to do torch vision dot. But I'm not sure what it means in the cell above it.
Oh, torch vision dot datasets and then dot USPS.
We have, like, we don't have the batch size, test batch size.
Oh, test batch. Oh, for that one, we'll cover it later, like after this one, I guess. Is the instruction clear, or would you like me to give them more questions? Or go over the solution?
I mean, no, that's good. Import modules. I'm down to go over that
Oh, okay.
whenever you.
So does anyone want to volunteer for like your solution code? So does anyone have any, oh. Does anyone have any questions? So far? Good. Oh, okay.
I need like type something.
Oh, no, no, I typed something here. Yeah.
So we can launch what depends on people that thinking like life for this one as well. And then Yeah, okay. I guess we can start. Okay, so here for the first one, it will probably look something like this. So it will be, since we imported, so first you have to import something from Torch Vision, and that's called torchvision.datasets. So we first import that. And then for our USPS dataset, you can call it through datasets.usps. So how you know that is by searching for Torch Vision datasets. Torch Vision datasets. So you first search for Torch Vision and then datasets and then USPS. And then you open it. So here's like a description for what the USPS like data loader or like the class itself contains. So from this one, you will want to like get comfortable with reading something like this. So the first thing is remember we said about like whether we want it to be training data or testing data. So here you can find something called train. And then from that, so you see it's a Boolean. So how you will want to differentiate your testing and training data sets is by so you basically call torchvision.datasets.usps. And then for the two of them, one will have train equals true and then the other train equals false. Yeah. And then the other thing is something called download. So here, so remember for data sets, sometimes we either download them ourselves or like the function will download for us. So for this case, we're really fortunate in the case of that. For this class, you can specify download equals true. So what this means, it says if it is true, it will download the data sets into the directory that you specifies. So how will we know where it will be downloading the data set? So for this one, you will have to look at the path, the route. So here is the route, and then so for the route, you will be able to specify like where you want to store it. Yeah.
Does that make sense so far? Okay, so I guess so for this one, there's different ways of saving like the data sets, but right now we can type it as list. Or you can also type it as since there might be collision for these ones because they're all being downloaded to the same thing. What you can do is you can say like, so we can first write dot, so that's like the current directory, and then we can say data and then train, and then the other data and then test, so that they are being saved to two different folders. Does it make sense so far? Any questions?
What about the earlier things, like, you know, you screw out like batch size test, batch check, I'm not gonna happen.
Oh yeah, I'm gonna cover that. Sorry, because I was like, this might be more important, and then after that we can then like loop through after this. Yeah. So does anyone know what a data loader is? Okay, so a data loader defines, it's like a class of like how you want to be reading your data set. So there's something, if anyone is interested, you can go to a tutorial called Create Your Custom Data Loader. Let me open that. Custom Data Loader. So this will probably be pretty helpful when you're like using your custom data sets. So that like so first data sets is like, it will store like how where your data set itself is, and then like the training data and testing data. And the data loader is how you will want to load each data into your machine learning model. This is because for each data set, there will be different kinds of way to like load them, because data are all different. For example, like images or like audio, you want to load them differently, right? Because like their format are all like really different. So within like a data loader, awesome. It will define something, for example, like the length. For example, if you want to know how many samples, I guess, you have in the data set, for each of the data, depending on like their data set format, it might be different. And then how you will be getting each item, like each sample will also be different. So I guess if anyone is interested, like look up how to create custom data loader. But basically this like this creates like a layer of like abstraction for the machine learning model to just call like the data loader and then get the sample that they want for each of the data, so that it's really easy for them to loop through each data within the data set. Okay. So for the data loader, there's another thing that we need to import. It's called the data loader from Torch Utils. So you will probably create something called torchutils.data.data loader. So let's type that out. And then after that, you will have to put in the data set that you just defined here inside. And so here you can see like all the different things that you can define for this data loader. So for the batch size, let me like specify like a random batch size, and then I will go through that after I talk about data loader. So for batch size, let's do something like 32. And then for the shuffle, what we meant by shuffle is this will make sure that whenever you're getting like for example, a batch of data, like for example, like 10 samples within a batch or something, you will make sure the order are like different. You'll shuffle the order so that like the machine learning model don't like secretly remember the pattern of like how they are being administered. It's a bit like when you're given like a test, sometimes your professor will like randomize like the order where they are being administered on the exam. So it's a bit like that. So for the shuffle, we will usually want to be true. So we can define shuffle equals true.
You want to do that regularly, usually?
Yes. So this usually helps them like, so let's say there's like you load like a batch and then they are like the same set. You want them to usually appear in different order so that they don't like, yeah. Yeah, they won't be like in this specific order of the questions, I would answer like XYZ. Yeah. And then for the test loader, it will be really similar. So I will copy and paste this, but the only difference will be test. So you will change the data set that you will be loading for test data set loader, test loader to test data set. Okay. Okay, so yeah, someone was asking, yeah, sorry for skipping to this part, and I think I'll go back to like the previous cell right now. So here remember we have like different device type, right? So oh, let me go over the batch size. So does anyone remember what epoch or batch is? Okay, so when a machine learning model is being trained, there's something called like epoch and batch. So this is because data set is usually really large. And then so for each batch, it's like how many data samples you want to be loading for each time. So that the machine learning model will not be loading the entire data set because that's too much. It's a bit like when you're, for example, revising for midterms right now, you will usually want to like do a few questions at a time instead of like doing all of them like the night before or something. Yeah, so that's why we want to do batch so that they learn like incrementally instead of like learning everything all at once, because that will like their memory will be overloaded and it will not be really it will be really slow in this case, and then the learning will also be pretty bad. Yeah. And then the other thing is called the epoch. So what epoch means is how many time you want the model to go over the data set. So I guess making an analogy again is how many times you want to go over, for example, your textbook when you're doing revision. So for example, like if you only read through like your class content like once, you'll probably not remember them, right? So you can specify like how many times you want your machine learning model to go over them so that they actually learn the things and then like actually transfer the things they learn from this data set to like test data set. Yeah. Okay, so here's the batch size, and then here's the test batch size. So they're just like two different constants for you to define for like your test data set and for your trained data set. Yeah. Okay, so I guess a few caveats for this is usually how much you want to define for the batch size. This is called a hyperparameter. So this will affect your machine learning models like final performance depending on how you define this. But then one big thing for how you want to define them, what's the sound? Oh, how you want to define them is based on how powerful your GPU is. So this is for example, if your GPU is like, for example, the T4 GPU that we have for Google Colab, you probably want it to be like the batch size to be small because it doesn't have that much of memory to like load all the data like all at once. It will like overload or something. So usually it could be something like 16 or 32. So let us define that. I will do 32 for both right now. Oh, and then by what I meant by hyperparameter is like this is usually like you have to like go try each of the hyperparameter and then do like test them out for like each model to see like which kind of hyperparameter value is like the best. Okay, so the other thing here we have the train KW args. So this is kind of hard to pronounce, but what this means is keyword arguments. So here we want to separate the keyword arguments for testing and training. Yeah, so here I included the comments for what they each mean. So this would probably be useful when you're like deciding the configuration of like which device you're running on and then like what batch sizes you're running on. Yeah. Okay, so I guess since we're doing this, now let's go back to the sites to learn about the torch device things. So here we have something called use CUDA. So CUDA, does anyone know what CUDA is, I guess?
I mean, it's the use of the GPU, right?
Yes,
Um,
NVIDIA's
it's an
GPU.
NVIDIA thing.
Yes,
Yeah.
no AMD GPU, I
No,
guess, in this case.
Yeah.
We hate AMD.
We
No.
don't-
Yeah, so sorry. Yeah, so here you will say like whether you want to use CUDA. And so we have a function. So this is one of the configuration that you want to include in your keyword arguments. So how you will do that is, so right now, so you might not know how to do this. So I can go through like how we can find it. So the final thing you want to do is torch is CUDA available, but how can you find that function when you're like coding PyTorch yourself? So you can do this. So search for PyTorch and then CUDA available. And then you'll find this function. So this will probably be the function that you want to use. So it will check whether there is CUDA, like whether you have dedicated NVIDIA GPU on your computer. So you'll want to run this function here. So this will return a Boolean. So this is like the correct one for our exercise, because here we have a hint of it's a Boolean type. So you will do this. So this will basically say like, yeah, like it's CUDA available. Do you have GPU? Okay, so this is like not important. So for the training arguments, it will be like a set of dictionaries. So I guess we can define that first. Oh, are we going over time? Oh, it's 3 minutes until it ends. So I guess you can do batch size. Oh, does anyone know what dictionary is in Python?
It's just an attribute.
Yeah, okay, so it's like key value pair. Yeah. And then the key should all be unique. Yeah, so here, does anyone know what the key is in this case? Yeah, batch size. Okay, so this is the key, and then this is a value. Yeah. And then so the reason, so here, for test keyword arguments, we want a different batch size. So does anyone know what the value will be for the variable?
Um,
It will be test batch size. You will use this variable instead of batch size. Yeah, okay, so let's define that. I guess we're kind of running over time. Does anyone, do everyone want to like stay for a little bit longer, or do you want to like we go over this next time? Oh, okay, you're all like, I want to learn. I think. Okay. Okay, so here's like the parameters, and then what's the other parameter? Here is use CUDA, which you will have to update. So here you will say like, oh, sorry, no, for use CUDA, you will have to use this to decide which device type that you want to use for your training. So for device type, CUDA is one of them, and then the other one is CPU. And then there's also another one that comes out like in recent years that called MPS. So MPS, that one is for like Mac users. So you can look into that if you want, if you're Mac users. So here what we'll probably do is we'll write like in like conditional statement to decide which device type that we want to be using. So So it looks something like this. Like really simple, I guess. And then you will add that into here. Okay, yeah. So I guess these will be a few arguments that we will want to set up. So let's run them first. This is the conditionals that we wrote in the previous part. So here, when we're running the train data, oh yeah, then please ask your question.
Why do you not why do you not like establish any other user value? Like besides, like what do we do today and device?
Oh. Oh yeah, so we use something called, we decide the device based on that. Yeah. Okay, so here, we see that it's downloading the data set. Since here we specify like download equals true. And then I think another thing I forgot, is the transform. So when we're specifying the data set, one thing we can do is, we can specify the data, whether the data set needs any transform. So you can find that through here. So in our torchvision.datasets.usps, you can see there's one parameter called transform. And then this will be the transform that we defined, like you defined in the first workshop. So you will have to go here. And then for the transforms, you transform equal transform. So for me, I think I defined it as transforms. And I'm gonna scroll back just to make sure. Oh, sorry, it's without this. Okay. I think we probably should like stop right now so that we can continue later. But if you guys have any questions on like any of the collab parts, like maybe DM us on Discord or like go on the ACM AI Discord server. Yeah, I think that's it. Thank you.